All right, good morning, everybody. Happy Monday. So I guess just one announcement is I have a new assignment up on Canvas. I'm probably going to make a supplemental video that covers the assignment since I won't really have too much time to cover it because I want to make sure I get through sort of these last two algorithms this week for graph theory. And that way, next week, Monday, will be an exam review. And then next week, Wednesday, not quite sure if I'll have extra material or just maybe have that class just canceled so you have more free time to prepare for your own exams for this class and for other classes as well. So we'll have a class this week, Monday and Wednesday, because I think Wednesday, 8:30 is a morning class and it's also online. So I don't think it's going to affect any Thanksgiving traveling. I don't think, but if it does, well, I guess it is going to be recorded, so you can always watch it like that. But for the morning class, I don't think it'll be affected. I don't think, at least. So I'm going to go ahead and just go on a limb here and say that Wednesday we'll have a class, and then next week Monday will be exam review, and then Wednesday after next week Wednesday we'll see what happens there. But either way, just to kind of keep up pace and make sure I don't fall behind, I'll just make a video on the assignment. So I'll have it up hopefully today. Worst case, it'll be tomorrow, but hopefully I can get that. I'll have some time to get it done today. So anyway, um, let's go ahead and just begin a screen share and let's continue from last time's content. So I believe I talked about Dijkstra's algorithm a little bit, so I'm going to do an example of that today. So let's go ahead and begin our screen share. All right. So we last left off on this portion here. So basically for Dijkstra's algorithm, we have this function here, very similar to breadth first search, except that just a little different, but very similar type of idea. So I guess the pseudocode's right there, but I think the example I'll show is going to really make more sense. So I'm gonna go ahead and do an example right now and just sort of, kind of paraphrase the pseudocode as I go over this example. So let's go ahead and just start with that first. So let's, I'm going to go ahead and put a line over here and begin the example on Dijkstra's algorithm. So I'm going to just draw my graph. So let's see, I guess I'm going to just, let me see, I have an 8 node graph, should be enough to kind of really go over this. Let's pull this up. Two, three, five, 6, 7, and maybe 8. Okay. So I'm going to use numbers to ID these nodes, but for assignment 9, as you can see, we're using strings to ID the nodes. So a hash map is going to be used because each index is not going to be a number, it's going to be a string. So a hash map is kind of like, think of it like an array where the string, the node name, is going to be that index. That's why we're using a hash map for assignment 9, basically. So anyway, let's go ahead and let me just sort of put the lines over here. Kind of hard to draw a structure. No, never mind. I can use this approach. Okay, I can draw lines like this, which is way nicer. So it's going to be a directed graph we'll use. And let's see. Put this over here. And then I'll just add some more edges. One over here. 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 Let's see what else. What else can I do? Could try something like this maybe. So let's see. No, that's not what I wanted it to do. I guess I'll go ahead and I'll put some more edges like this. Let me try to go back over here. Let's see. Let's try this. Let's try this. Let me go ahead and try to, let's see, I can try and make a line that's going to go all the way from 4 to 3, but I may have to not be a nice line like this. I'll have to kind of make it a little different. I guess, and 3 may go back to 1, I guess. I think that works. I think it's a decent graph. So let's go ahead and add in our weights. I'm going to use, I guess, green to draw the weights in. So we're going to first have perhaps, let's say we'll have a 2 over here. Let me see. Maybe I'll have like a, hold on. I'll have a 1 over here, 3 over here. Actually, I'll put 4 here. Now I'll put a 2 over there. Then I'll go ahead and I'll put a 1 here. I guess this will be then 2. Then I'll have, let's say I'll have perhaps 3 here. Try to make this graph interesting where it will cause some chaos, but it's probably not a chaotic enough of a graph, maybe. Maybe I'll try to put an extra edging over here. Let's try 5. Yeah, I think this will be a little better. Let's see, I may add another edging over here just to make things more interesting. Okay. Let's see if I can make this interesting. So I'll put a 1 over here so it's closer to that. Then I'll say like 3 over here, 1 over here. I'll put another 1 like that. And then I guess I'll just try, let's say 7. Then I'll try 3, 2, 4. Maybe I'll try 6 over there. Okay, so there we go. So here's our graph. I'll put this number closer to this edge so we don't get confused here. So basically we have our graph right here, and we can notice that we have these weights associated with every edge, basically. So for Dijkstra's algorithm, we're going to try to find the smallest weight path from a start node to all nodes in our graph. So we're going to choose 0 as our start node just because. Now, if I want to have the smallest weight path from 1 to every node, I would just have 1 be my first node I would start with. So I'm going to choose 0 just because. So the first step we're going to do is we're going to insert into our heap. So our heap is going to contain S0, and in our weighted array, which let's see, we have an 8-element array, so I'm going to draw that shape right here. And we're going to have, let's see, we're going to have 7 lines. Like that. And we're going to have the array brackets. I'll use S, A, B, C, D. Oops. Oh, I should have actually used letters instead. My mistake. Otherwise, it'll be confusing when I do weights. So I'm going to go ahead and just use letters instead for the node names, just to make it a little easier. My mistakes. I'm going to use this will be S. This will be A. This will be B, C, D, E, F, and G. Yeah, it makes it less confusing. So a number represents a weight of a path, and a letter represents the node, so it won't throw us off. So then we're going to have our weighted array is going to be labeled as this. So just for now, we're going to have this previous hash map, but perhaps that's going to just basically allow us to map a letter to a value. So I'm going to go ahead and put the graph back so you can copy that down if you need to. So initially in our heap, we have S with the weight of 0 is going to be on our heap initially. So that's going to be our starting node. So think of the heap as like your first and first out queue when doing breadth first search. So heap will be our queue essentially. So you first push S with the weight 0 onto our heap, and then we're going to start with this. And our weighted array is going to contain all infinities at the moment, which really implies that we have not found a weighted path to any node yet. So let's go ahead and do our first step. So step one, we're going to first, of course, pop our heap. So, or pop, or delete, min, whatever you want to call it. We're just gonna extract the smallest element, which is going to be S0. So we're first going to extract S0. When we do that, I'm going to go ahead and write my W array over here. I should have copied all of this. Let me just go ahead and just put W first. And I'll just paste the array next to it, so I don't have to redraw it every single time. Oh, actually, never mind, I already incorporated the W. Oh, okay, perfect. So I'm going to go ahead and just paste that over here then. Okay, I don't know why OneNote's doing this. Oh, no. Okay, I think it's okay now. All right, cool. So what's going to happen when I go ahead and I pop S off of the heap, it's going to write 0 into this S position because S was popped off. So now we have our shortest final weight. So when we write an element, we write into this W array. That means we found our best possible path weight to that node. So we're going to first write S0 into our array, which 0 implies that our shortest path to S is going to be 0, which makes sense because we started from S. So I'm going to go ahead and go to the top and just put that 0 right here to denote that's going to be our path weight. And now we're going to try to weight all the neighbors of S. So we have A, C, and D as our neighbors. So let's go ahead and check this out. So let's first look at A. So our path weight S is going to be 0 plus the edge weight from S to A is going to be 4. So that means, that means A's weight is going to be 4. So we're going to insert that into the heap. I should have put this below. To be consistent, I'm kind of a little bit rusty right now. So we're going to have our heap above, and A4 is going to be inserted. This is kind of our relaxation step because A was not in our heap yet. So we're going to have the weight of 4 for A and insert it into our heap. Okay, so our next neighbor of S is going to be C. So S has the path weight 0 plus that edge weight from S to C, which is 5. So we're going to insert C5 into our heap. So of course we'd insert it and we'd bubble it up. Now, you don't have to actually show the actual elements in that heap order. All you have to do for like the exam is just sort of tell me what nodes are currently in the heap. And of course, you can eyeball which would be the smallest element to be removed next, which we'll get to that in a second. And after this, we have the neighbor D from S. So S has the weight of 0 plus the edge weight, which is 1 to D. So 0 plus 1, then D has the weight of 1. So we insert D onto the heap. Now, of course, if we had an actual min heap, like it would actually bubble D1 up to the front, obviously. But for now, we're going to focus on just what nodes are currently on the heap, and we'll be able to eyeball which one will get popped off next. But of course, D1 would bubble up to the front. If we actually drew out the actual heap after every insertion, we would know D1 would bubble up, obviously. So anyway, this is going to be the result. After we pop S from the heap, this will be our weighted array. And it's going to be our current state of the heap after we processed this node. Okay, so the next step we're going to have to do, we're going to have to pop the next smallest weight off of this heap. So just as I said last time, it's a greedy algorithm. So the next smallest element is going to be D1. That's going to get popped off. And of course, you can imagine that in a min heap, D1 would be the root element of this potential heap. So D1 gets popped off next. So you always pop the next smallest one off every single time because it is, after all, a greedy algorithm. And our heap currently will have A4 still and C5, but D1 was popped off. And of course, I'm going to paste the array, the weighted array, right next to this. So S has the weight 0, and then D is not going to have the weight 1. So we pop the element off of the heap. So whatever weight that node has, that will be its final weight. It will never, there is no way we can get a better weight. So I'll kind of explain a proof of this towards the end. You can somewhat prove this using some type of a contradiction proof that there can't be a better possible weight. But for now, we'll just believe me right now. But of course, I'll do my best to kind of convince you that it will be the best possible weight. So D has a weight of 1, and the rest will be infinity because we have not processed any of these yet. They could be on the heap, some of these nodes, but we haven't processed. We haven't gotten the best possible weight yet. We had the best weight from S and for D so far. So I'm going to write 1 over here. That's going to be the minimal path weight from S to D, which weight of 1. So now let's look at all of D's neighbors. So D has a neighbor A, and A is not processed. So let's take a look. So D has the path weight of 1 plus the edge weight 2 to A. So that means we have a path weight to A that has a weight of 3 currently. Because, okay, right now we have weight 4, but we just found a better one. Because D has the weight of 1, that path weight, plus the edge weight A is 2. So we're going to go ahead and relax this, this weight because we found a better one. So relax means either we insert a new node onto our heap or the existing node in our heap, we're going to update that weight and bubble it up. Now, of course, in order to make this work quickly, you have to have another structure that can tell you what index in the heap array does that node A reside in. So if you don't want to search through the heap and find A, you want to have another array that maps all the elements in this heap array so you always know exactly which element A is going to be in. So for now, we'll just say it's going to magically just automatically know where A is, but you have to maintain a different structure. That would have to be like a shadow. It would shadow the heap array so you know exactly what element A would be in. So you can quickly, in constant time, locate A, update that node, and then bubble up that value. But that was a relaxation because we found a better path to A. Now, same thing. D has a neighbor that goes to C. So right now, D has the weight 1 plus the edge weight from D to C will be 3. So 1 plus 3 is 4. And it's actually a better sort of weight than we've seen so far because C has a weight of 5, but we found a better weight. So we're going to go ahead and reweight this to 4, which will be a relaxation step because we updated a better path weight to C. So whenever we insert a new element or if we update an element in our heap, that's our relaxation step. So of course we update C4, and then we try to bubble it up if it can. In this case, it wouldn't be able to because A3 would be smaller, obviously, but we have to still attempt to bubble this up. Then D has a weight that goes to F. So D has a path to F as well. So we're going to say, well, D has the weight of 1 plus the edge weight to F will be also 1. So 1 plus 1, 2. And F is not in our heap, so we're going to insert F2 into the heap. And of course, it would bubble up to the very front of our heap, obviously. I'm not going to draw that, but you can imagine it would bubble up to the front. Let's take a look at the question. So let me see, because A had the weight of 4 earlier, because earlier we put A4 onto the heap because S had a path weight 0 plus 4, because the edge weight was 4, so it gave us a 4 total. And then we popped D off of the heap, we're trying to reweight all of D's neighbors. So one of these neighbors was A. So we have a path weight. So D has the path weight 1 plus that edge weight from D to A is 2. So 1 plus 2 is going to be 3. And we simply compare 3 to the previous weight. So A had the weight of 4, but now we found a better weight, which is D, which is 1 plus 2, 3, which is better. So we're going to just update A from a 4 to a 3, and then just bubble up a 3 in our heap. So there's no subtraction. We just add the path weight D1 plus the edge weight from D to A, which is 2. Okay, cool. So let's go ahead and continue with this. So now the other neighbor of D is going to be G. So G is not in our heap currently. So this is going to obviously be the best path weight so far. So G has a weight of 1 plus the edge weight from D to G will be 3. So 1 plus 3 will give us 4. So we're going to insert G4 onto our heap. So the heap kind of maintains the current nodes waiting to be processed. So we have these 4 nodes currently in our heap, and we're going to try to process a node. So let me just make sure I didn't skip anything. So I think D only had neighbors A, C, F, and G, and that was it, I believe. Okay, perfect. So now, given our current circumstance, we're going to have to, of course, just like with breadth first search, we stop once our heap is empty. Obviously, your heap is not empty, so we have to continue. So we're going to pop the next smallest element off, and F2 is our next smallest sort of path weight. So we're going to pop F2 off of the heap. So our heap currently now will have, of course, A3 is still going to be on there. C4 will be there, and so will G4. And then our weighted array, I'm going to go ahead and paste this here. So we had 0 for S, D had 1, F has 2. So we're going to go ahead and write F2 onto this weighted array, and the rest will be infinity. Every time you pop an element off of the heap, we're going to write that weight into our W array, which means that that's going to be our best path weight from S. So right now, from S to D, the best path weight we have is 1. And from S to F, our best path weight we have is 2. And those will never update. Once we pop off of the heap, that's the best path we could find. We'll prove that that's always going to be the case. So now we're going to try to reweight all of F's neighbors. So I'm going to write 2 over here now because F's weight is now going to be 2. It's never going to change from this point on. It's going to always remain 2 from this day forth. So let's go ahead and reweight all of F's neighbors. We only have one neighbor for F, which will be G. Okay, so F has the actual path weight of 2 plus the edge weight from F to G will be 1. So it's going to be a total of 2 plus 1 or 3, which is a better path weight than we had before. Because G, we had currently had 4. Well, now we found a better one, which is going to be 3. We found a better path weight from S to G. It goes through F. So just like this example I drew this picture over here earlier, this is the idea. Because so far we had a path from S to G that went through some nodes, but I found a better one. So from F to G, it's a better weighted path actually than from D to G. So F to G was better. So we're going to actually select this one instead. So we're going to update G to be 3, and of course it would bubble up in our heap. And for F, that's the only neighbor we have, so that's it. Now, I guess here's a case where we have a little bit of an impasse because now we have A3 and G3, which one gets popped off next? And the answer is it doesn't really matter which one. So for your exam question, I'm going to make sure that this can never happen. We're never going to have a case where we're going to have a tie for the next best sort of weight. That way, there won't be too many possible answers. I want to make sure there's only one possible answer for everybody so it's easier to grade. But obviously, I could pop A or G off. I'll pop A off next because I guess A is early in the alphabet than G, so that's how I'm going to break that tie, I suppose. But on the exam, though, this won't happen. I'm going to make sure that we can't have a case where there'll be a tie like this. I'm going to go ahead and pop A3 next, our next smallest one. And our heap is going to have C4 and G3. And our weighted array is going to be this. So we're going to have 0, and then A will be 3. I'll make it capital. A will be 3, and then D will still be 1, F will still be 2, and the rest will be infinity. So you pop A3, we're going to write that to our W array, and now we're going to try to look at all of A's neighbors. I'm going to go ahead and put 3 over here because now this will be the best possible weight. So we're going to go try to reweight all of A's neighbors, and A only has one neighbor, which goes to E. So right now, the weight of E is going to be, well, the path weight of A, which is going to be currently going to be 1, or sorry, 3, my mistake. So path weight is going to be 3, plus the edge weight from A to E is going to be 1, so 3 plus 1, or 4. So we're going to insert E4 into our heap. That's the only neighbor, I believe, for A, so I think we're done with that. So that's all we're going to do right there. There was nothing else. I think A has no other outgoing neighbor, so that's it. So we weren't able to update anything, but we were able to at least insert onto our heap. Okay, so we have that. So step 5, we're going to, again, of course, we're going to pop the heap again because our heap is not empty. And our next smallest edge weight will be G3. So we pop G3 next off of our heap. And of course, I'm gonna go ahead and write the heap next. So our heap will now have the following 2 elements. It's gonna have C4 and E4 like that. I'll write my weighted array. I'm going to just paste the weighted array over here. We're gonna have 0, 3, B will still be infinity. C is infinity, D will be 1, E is now going to be infinity still, sorry, and F will be 2, and G will now be 3. So now we found the shortest minimum weight path from S to G. It has the weight of 3. I'm going to, in my picture, put the 3 right over here to denote that we found our best possible path. So okay, so I guess this is gonna get a little boring here. We have not much left to be done, but it's a possibility. So this could, of course, happen. So now we're going to look at the next neighbor. So we'll look at all the neighbors of G, and G only has one neighbor, which goes just to B. So we're gonna see. So B was not inserted into our heap yet. So we're going to look at the pathway to B. So of course we take the pathway to G, which is 3, plus the edge weight to B, which is 2. So 3 plus 2 is 5. So we're going to insert B5 onto our heap. That's the only thing we can, that's all we can really do, I believe, because there's no better, there's no other neighbor for G. So that's all we're going to do there. So that's going to be our current heap. Once again, we have C4 and E4. So we're going to pop one of those two. Well, I guess I'll pop C4 since C is earlier in the alphabet than E. So my tiebreaker will be that, I guess. So the next step is, since our heap is not empty, we're going to have to pop our next smallest element. So C4. And our heap is going to contain currently E4 and B5. And I'm going to then, of course, paste the W array and write to this array because we just found a new pathway. So we're going to have 0, 3, we're going to have infinity over here. C will have 4, 1, infinity, 2, and 3. So when we pop element C4, we're going to write that into our weighted array. So now we found our best possible pathway from S to C. It has the weight of 4. Now let's go ahead and reweight all the neighbors of C. So C has the weight 4. I'm going to write the 4 right over here, just like that. And let's look at all of C's neighbors. So we only have one neighbor in this example. So right now, C has a neighbor that goes to B. So we're going to have C with the weight of 4 plus the edge weight from C to B, which is going to be 6, so it's 10. And it's actually not a better pathway than we have seen before, because B has the weight of 5 currently. So going from C to B is another path, but it's not a better path. So we're not going to do a relaxation right there. So you only do this only if you find a better pathway, or if, let's say, B wasn't on our heap already, then of course that's the best pathway so far because there is no other pathway. But right now we already found a weight so far to B, and it's better than 10, so we're not going to update B's weight through C, because that would not be a better weight. So nothing happens there. So nothing updates right now. So now for step 7, we're going to have to, our heap is not empty, we're going to have to pop the heap. So I'm going to pop B5 next. I guess since B is earlier than E in the alphabet, just pop B5. Oh, actually, no, sorry. I can't do it because E4 is actually smaller weight. It's not a tie this time. It's my mistake. So E4 is popped off because it has the smaller pathway. So of course, I only use that lettering, the early alphabet, only on tiebreakers. But right now there is no tie. E4 is the smaller pathway. So I'm going to basically pop E4. And now my heap currently contains just a B5 and my weighted array. I'm going to update this weighted array next. And we're going to have 0 for S, then 3, infinity, 4, 1, 4, 2, and 3. I'm going to now write the 4 next to E in my graph. So now, looking at all of E's neighbors, E has neighbor goes to D and to G and to B. And looks like for D, we already processed D. So now we're not even gonna try to try to reweight this, because we know that since D's been processed, because index D in our W array has a value that's not infinity, which means we know that D has been processed already. So there's no point even trying to look at that edge that goes from E to D. So forget that. E to G, same idea. There's no point looking at that either because we already processed G. Now B has not been processed yet, so maybe we find a better path to B. So E has the weight of 4, plus the edge weight from E to B is 3, so a total of 7, and that's actually not going to be better than our path weight we found currently. So B has a weight of 5 currently. Going from E, it will not be better because the path weight, which is 4 to E, plus the edge weight 3 to B is not better. So we're not going to relax this node because we did not find a better weight to B. So, oh well, nothing happens here either. And then for our next step, since our heap is not empty, we're going to have to, again, pop our heap. And of course, we have one element in our heap, so pretty simple to pop right there. Let's pop our only element. And our weighted array, I'm going to write this W array right over here. And S has the weight of 3. A is, oh, sorry, S is 0, my mistake. A is 3. B will now be 5. And then we're going to go ahead and copy the rest. Let's try to reweight all of B's neighbors, although there shouldn't be any, but let's just take a look anyway. I'm going to write 5 over here. That's going to be the best path weight to B. So B has only one neighbor, it goes to A, but we already processed A, so nothing to see here. And that's the only outgoing neighbor we had, so that's it. And our heap now is going to be empty. So we are now done with this algorithm. And this W array is going to give us the best path weight from S to every node in my graph. So S to A has a weight of 3, that's the best path weight. S to B has the best path weight of 5, and so forth. That's going to be our solution. Now, of course, we could maintain a predecessor array as well if we wanted to. So we can actually construct the actual path that has the minimal weight from S to that node. So I want to compute the best path. So let's say the path from S to E has 4. I could output the actual path as well. All you have to do, just like with breadth first search, I'm going to scroll up here for a second. When we do a relaxation, like over here, all we'd have to do right now, so I'll put this here just because I'll put this here in red. We could go ahead and say predecessor of V equals U. I would go ahead and add that statement into both of these if statements, which means that if I found a better path to V from U, I would write predecessor of V, which would be U. That means we came from U to get to V, basically. So that's sort of the idea here. So yes, so represent infinity, you'd have to maybe use -1 would be a bad idea because -1 would be, well, I guess, yeah. So some type of, we want to have some type of value to represent that we have not really written anything to that element in the array. So we would use maybe some type of really large number, something we would use basically just to kind of represent that it has not been processed yet. So it's up to you how you want to do that. It just, but yeah, that would be a good idea though. So, yeah. All right. Yep. Okay. So, I mean, I'm not going to focus on the actual predecessor array, but all you'd have to do is when you do a relaxation, like for example over here, when I had my current weight from G, which was 4. So let's say over here, for example, I had the predecessor of G was D. When I first inserted G onto my heap with a weight of 4, it went from D. So G's predecessor was D at this point. When I popped F2 off of the heap, I found a better weight from F to G because F has a weight of 2 plus 1, which is going to be a total of 3. Then G's predecessor would now be F from that point on. Whenever we relax a node, we're going to update the predecessor as well if I wanted to actually construct the actual path as well. But for the exam question, we're going to focus mostly on just getting the path weight from our start node to all of our other nodes. So the same idea with breadth first search. This is not going to find the best path weight necessarily from any two nodes. So the best path from C to E, well, this may not find that. This only finds the best pathway from S to every node. Now, if I wanted to find the shortest path from C to every node, I'd have to basically run Dijkstra's and initially put C2 onto my heap and then start from there. But because I chose S0 as my first initial element in my heap, that means it's going to find the best path from S to every node. But of course, I could have chose maybe F as my starting node. So I'd put F0 onto my heap initially, and then pop F0 off of the heap, and then do it like that instead. But I chose S just because. So that's all. Let's go ahead and write some notes on this. Oh yeah, of course. So maybe before I move on, for the exam question involving Dijkstra's algorithm. So basically, you have to show me this. So step 1, step 2, step 3, you have to actually show me this. Now on the exam, since you're gonna be doing it on the lockdown browser, you don't have to actually put that /3 over here. Let's say, for example, right here. You could just put A3 there instead. I put that slash there so you can kind of see what happened for learning purposes. But of course, for the exam, just put that there. So all you have to do on the exam is put that number 2 right there, and then which nodes popped off, and then show me the heap after you relax all the neighbors of that node, and then show me this W array. Now, of course, for the exam, showing this might be kind of a little bit of work. So you could do on the exam is the following. You could have W equals, let's say, 0, asterisk, 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 1, asterisk, asterisk, asterisk. You can show me this on the exam, which means that S has a weight of 0, and then we have A, B, and C will be infinity. Then D has the weight of 1, and then E, F, and G all have infinity. So using asterisks to kind of denote that. So you can actually show me this on the exam. So on the exam, you have to basically maybe just say pop D1. Show me this. And the actual heap array itself, you don't have to show me any particular order. Just make sure all the nodes are in the heap that should be in the heap at that point in time. So that's what you do essentially. So for exam, now of course if you want to show this this sort of W array in that nice array format, that's also fine as well. But whatever is easier, but make sure it's clear to me that you have the steps all lined up. But that's what you have to do for the exam. And this question, typically students don't make any major mistakes. Just, don't try to rush this question because you want to make sure you don't get it wrong. I think students in the past will make a mistake because what happens is there could be a very long path that happens to be the shortest possible path. So for example, let's say S to B, the best possible path could be, maybe I could have gotten, let's say, S to A to E to G, and G to B could be the best possible pathway. I could draw the edge weights up in a certain way where a very long path actually ends up being the shortest weight path from S to B. So be very careful with that. Don't try to rush this. Also on the exam, I won't be able to give you a picture like this because for a lockdown browser, it's going to, knowing my luck, it's not going to render the JPEG or the PNG on the lockdown browser. So what I'd have to do is I'd have to go ahead and give you an adjacency list I'd give you basically. Let me go ahead and sort of draw the adjacency list up as well, so at least you have an idea. We started from S just because I chose S as my starting node. There's no reason why I chose it. I could pick any node for my start, but I just chose S just because. And for exam, I'm going to go ahead and tell you use S as your start node as well. There's no reason why I chose S. So basically, for the exam, I'm going to go ahead and tell you what's going to be on the exam. So I'm not going to give you a graph like this because I know it's going to not render on the lockdown browser. I can already tell you right now because, of course, there's no reason why. It just won't work. And just to make life more difficult for everybody, it won't work because it has to do that. Lockdown browser has to make sure to make life as difficult as possible for everybody involved. I mean, without that, we can't really, have a semester of school without having something go wrong with the lockdown browsers. So basically, you'd have the following. So go ahead and try to, so we have, let's say 1, 2, 3, 4, 5, 6, 7, 8 nodes. Okay, so 8 lines over here. 1, 2, 3, 4, 5, 6, 7, and 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And I'll just try to draw straight lines here if I can. I think it's a little bit too not really even. I can't draw straight lines. Good enough. So S, A, B, C, D, E, F, and G. S, A, B, C, D, E, F, and G. And for now, I'm going to go ahead and just put these dashes here for that main diagonal. And what would happen is you would go ahead and I would say S goes A with the weight of 4. S goes to D with the weight of 1. S goes to the weight of 5. And the rest will be dashed like that. I'll go ahead and do the whole thing. So A has an edge to E, which is 4. The rest are dashed. And then B has just 1 that goes to A with the weight of 7. Oh, my mistake. E has a weight of 1. My mistake. I'm sorry. A goes E with a weight of 1. And A goes to 4 over here, 5, and 1. Perfect. B has a weight of 7. Then C has the weight of 6 to B. D has has several neighbors. D has A with 2. D goes to C with 3. D goes to F with 1. Goes to G with 3, I believe. I don't think I missed anything there. And then E has the neighbor G and B, so G is 4. And B will be 3. F has the neighbor G, which is 1. And G has neighbor B, which is 2. Hopefully I didn't miss anything there. Correct me if I'm wrong, though. Of course, for the exam, be very careful. I'm going to spend more time than just this to construct this question. But anyway, you would get a question like, you would get this actually on your exam. So you'd have to go ahead and construct the graph. 1 E path. Okay, so E goes to D as well, I believe. Yes, E goes to D with the weight of 2. Thank you. So I would give you this on the exam. And of course, when you take an exam at home, you can on paper draw out this graph. I would suggest draw the graph out. Although you probably could get away without drawing the graph out because you can always, if you're starting from S, the neighbors will be A, C, and D, right? So you actually probably could even avoid drawing the graph out entirely, but you know, this is the best way to make this work because, of course, otherwise on the lockdown browser, it will not render this image. So this is the safest way to make sure we have this. So if it's a dash, that means there's no edge. And a number means that's going to be the weight. So S goes to A with a weight of 4. As if you look at this picture, S goes to A with a weight of 4. S goes to C with a weight of 5, and so forth. And it will be a directed graph to make it simple. So that means you can see here that A does not go back to S. There's no edge from A back to S. So anyway, yeah, that's going to be how I'm going to give you the question on the exam. I'll give you this list, adjacency matrix, sorry, like that. Okay, so let's go ahead and now go into a little bit of conceptual contents involving Dijkstra's algorithm. So let's go over some theory involving this. So, okay. So basically, let's go over sort of the proof that this is going to work. So I guess this will be the proof of Dijkstra's algorithm. Okay, so the previous suppose a node UW is popped off of the heap. So U meaning the that's going to be the node name, and W is going to be the weight of, so the path weight to node U. And then suppose that W, maybe I'll put a subscript, so WU is not the minimum path weight from start node to U. So if that's the case, so if it's not the best, so if this is the case, then U with the weight W U prime would have been popped off the heap earlier. Because the idea is that since we know it's a greedy algorithm, and we always pop the next smallest weight every single time, because we can assume that the min heap is going to work. So for this proof, assume that min heap works as expected. So because of that, it would have popped it off earlier. So that means, so thus, U dot or U colon WU would never have been on the heap. Remember, once we pop an element off the heap, we're never going to reinsert it back onto the heap. So remember from our examples, let's look at it just for a second here. When I popped B off of the heap, we had a path from B to A, but we already processed A earlier, so we're not going to reinsert A onto the heap. So because once it's processed, we don't insert it. So that means this element, U with this weight, WU, could never have been on the heap. So that's a contradiction. This is the same paradox like time travel, basically. So if let's say pop an element off the heap, it's not the best path weight, contradiction is, well, then it would have found it earlier. So if a better pathway existed, it would have already found it. It's like time traveling. If you could travel back in time, you already would have done that. Because, well, that's why time traveling is kind of a paradox, because you already would have done that if you could have done it. So same idea here. If you found a better path, you would have already found it by now. So if a better path already existed, you would have found it earlier than this. But this is a more of a formal-ish kind of proof, and because this works because it's a greedy algorithm. So since this is a greedy algorithm and no negative edges are allowed for Dijkstra's algorithm, the proof holds. So But then the deal is that this only works for a graph with no negative edges. So with negative edges present in a graph, it's possible to have a shortest path, but you would not be able to use Dijkstra's algorithm in that case. But anyway, let's not go over the case of why negative edges can't work. So no negative edges allowed. It's a very simple proof, actually. So to disprove something is very simple. So assume that there's going to be a negative edge. So if you assume that, and you find a contradiction, or find a what's it called? Oh, I can't. An example, but it's actually the word for this. It's okay. I'm gonna go ahead and think about the word as I move along here. Anyway, counterexample. Thank you. That's the word I was thinking of. Counterexample. You find a counterexample, that means you disproved it. So disproving something is very simple. You find one counterexample, and that's it. To prove something that works is always hard. You have to actually use induction or contradiction proof. You have to show that it works for every single case. But to disprove something is very simple. Counterexample for the win. So over here, let's think of the following example and show how with negative edges, it's not going to work, Dijkstra's algorithm. Okay, so we have, I guess I'll just have A, B, and C. Let's say we came from some node to get to A. Let's suppose we came from somewhere. So right now, let's say we have the following weights. So I'm going to have, let's say I'm going to have 2, 1, and I guess -2. Yes, that works. So let's say A has the weight of, I'll just say 0, sure, just because make things easier, or maybe I'll say 1. So the pathway from the start node to get to A has a weight of 1. So what will happen here is that you're gonna have, let's say, 2 neighbors of A, B and C. So C would have the weight of 2, and B would have the weight of 3, right? Obviously, C has a smaller weight, so we first would process C first, because B would have the weight 3, C would have the weight 2. So obviously, we would go ahead and insert C2 and B3 onto my heap, and C2 would get popped off earlier. And then C2 has no neighbors, so we're done. And then we're going to go ahead and pop B off the heap next, and B has a path to C, which is -2. And actually, that's a better path from A. So if you want to go to C, if you go from A to B to C, it's a better weight, actually, because 3 minus 2 is 1, so 1's a better pathway to C, actually. So this is a case where Dijkstra would not work, because it would pop C first, and once you pop a node off the heap, we don't reweight ever again, which means that negative edge, it's not going to work. Now you could say, well, couldn't we just reweight it anyway? Yes, if you do that though, then it causes more problems, because now what could happen is this. What if from C, there's other paths that go from C? You're gonna have to redo everything all over again. Because there could be, okay, find a better path to C, but then because of that, you found newer paths from C to somewhere else, you have to reweight all of those neighbors, and then the runtime is going to get hit pretty bad at that point. So you have to assume no negative edges to make this work. So there's your counter example. Here's a case where it's not going to work. So with negative edges, you can find, there is an algorithm that does this, but it's not Dijkstra's algorithm anymore. And negative cycles are actually, so let me go ahead and also illustrate this. So if a graph has a negative cycle, then a minimum path weight does not exist. And this is not just for Dijkstra's. So any shortest path algorithm that can possibly exist cannot work if a negative cycle is in your graph. So a negative cycle, think of it like this. Let's say maybe when you were younger, when I was younger at least, I go to school with a bicycle. And just assume that from your house to school, you go downhill, which means you don't have to really put any energy. You just let gravity do its work and just have it just take you to school. On the way home, you go downhill again. Just assume you go downhill again. And I think one time when I was younger, I kind of messed with this one classmate. I told him like, yeah, just go. I'm gonna go downhill from home to school. I'm gonna go downhill from school back to home. I could almost see something short circuit in his brain, and he was getting really mad and irritated. And I saw that, so I kept on messing with him. But no, it's of course you can't go downhill the same way. If I went downhill from my house to school, I can't go downhill again. That doesn't make any sense. But I think that person didn't get the joke. I was only messing with him, and he got like really mad about this. So I don't get people sometimes. But anyway, so the thing is that that doesn't exist. You can't have that situation. So this is actually equivalent to a perpetual motion machine. As you're spinning, you're gaining more energy, which would be awesome. That would solve the entire energy crisis and the whole climate change issue would be solved right there, or at least it would kind of partially be solved right there. But of course, that doesn't exist. So a negative cycle means you can't, there's no shortest path. Let me go ahead and show an example of that. So I'm going to go ahead and just draw a few nodes over here. Yeah, I think this is good enough. So we'll have this, and then I'll draw a line that goes all the way around. So you have S, A, B, and C. And I'm going to have, let's see, I'm going to have maybe 2 over here. Let's see, -1 and -2. So yes, so A, B, and C, that would be a negative cycle. I'll put maybe a 3 over here and a 2 over there. Sure. So what happens is right there, these edges right here. So maybe I'll go ahead and I'll just sort of highlight these. Actually, I'll keep it like this. So actually, I'll put it like this. So these edges right here, they form a negative cycle. If I keep taking a cycle over and over again, I'm going to get a smaller and smaller path weight, which means that if I take this cycle over and over again, I'm going to constantly get a smaller weight, which means that there is no smallest possible weight. A negative infinity is the smallest weight, actually, because, okay, I found a path weight from S to A. If I take this cycle again, the path weight will now be 1 less than before. I can take that cycle again and get 1 less. So I keep gaining more energy as I take this cycle. It's equivalent to a Robot Chicken where Mario found a trick where he can sort of keep hitting those boxes and he gets more and more coins keep popping up and he has more and more money because he keeps hitting that box and more money keeps on coming out just for free like that. And of course, at some point he ran out of money and then things became really bad. But anyway, the thing is that if you have this situation, there is no smallest possible weight because it's negative infinity. You can keep in a cycle forever and ever and keep getting smaller and smaller pathways from S to A, B, C, or even back to itself, even for that matter. So there is no solution in this case. So just to distinguish them, a negative edge is not okay for Dijkstra's algorithm. So I'll write this over. No negative edges allowed for Dijkstra's algorithm. A negative edge is okay in general, just not for Dijkstra's algorithm. A negative cycle is not okay for any algorithm because then there is no solution. There is no possible smallest weight path from a start node to every node. And just to repeat, Dijkstra's algorithm is only a single source problem, so it's not going to find the shortest path between every possible pair of nodes, only from a start node to every node. if I wanted every possible pair, I'd have to run Dijkstra's on every node, just like breadth first search. Okay, so just to kind of distinguish these two, it's negative edge, negative cycle are two different. They're different, so don't get confused by these. So on the exam, be careful with negative edge or negative cycle. They are different because this has negative edge, but there is no negative cycle in this case. This one has a negative cycle, so it's a bit different. Okay, so we're almost done with class. So the last thing will be the runtime analysis. So that's the last thing we'll do, and then we'll be done with class for today. So basically, the simplest way to do this is, so each edge, just like with depth first and breadth first search, each edge is looked at once. And for each edge, we're going to have to either insert or update an element on the min heap. Whenever we insert something onto the min heap, so every time you look at an edge, so when you look at an edge for a neighbor, that edge we look at is going to potentially insert or update something on our heap. So the heap at most contains at most v elements, where v is number of vertices or nodes in your graph. So every insertion or update will require a bubble up. In the worst case, has to bubble all the way up to the very top of your heap. So this is going to take basically O of log v time, and it's going to be E number of edges. So for every edge, we do this O of log v amount of work. So the runtime is going to be O of E log v, because we just basically all we do is we look at an edge, just like for breadth first search. The difference there is every edge you look at, it takes constant time. If we insert onto the first and first out queue, that's a constant operation. But a min heap is not a constant, it's a log operation. Now, of course, on Wikipedia, they might give you this. They might say it's O of, they might give you this answer, O of E, plus V log V. The purpose is that we could have a sparse or a dense graph. So it's V log V for sparse and E log V for dense. Either way, though, it really depends on the edge count. So E could be V or V squared. So really, it's just that edge amount that really makes a difference. I don't know why I had to overkill this so much, but it's just E log V. That's the runtime of Dijkstra's algorithm. So I guess that's pretty much it, I guess, for this. So on Wednesday, we'll cover the next, our last algorithm, which will be Kruskal's algorithm. I'll cover that content on Wednesday. And then, of course, we'll have Thanksgiving weeks. And then next week, we'll have a Monday class, which will be our exam review. And then Wednesday, we'll see what I do there. But anyway, for now, take care, stay safe. Thanks for watching. And I will see you guys next time.